Certo, estamos gravando.
That's a confusing word from for a Spanish speaker, aula.
Aula?
Yeah, which means classroom.
Yeah.
No, it's not a new aula for me. It's the same one it was yesterday and on Wednesday. Oh.
Então, por favor.
Yeah.
Obrigada.
So, last slide for this first course, and today we will go over the first two aulas. We will go through methods, and we will divide methods not so much by their purpose, they are for, but whether they belong to two main branches of statistics: description and hypothesis testing. It's, of course, really important to describe your data, to tell how they are. Particularly, we will be talking about the diversity. We'll measure diversity in different ways. But a different thing that will be the second lecture is actually interrogating your data, constructing a question in a way that your data can answer that question. And we'll see also that quite quickly we run out of options if we use the classical statistical methods of hypothesis testing. We'll see some. I think it's important in general, not in population genetics, but in any almost in any scientific branch, that that we know what does the p-value mean, because we live under the dictatorship of the p-value. We strive to get p-values below 0.05. So it's important to remember what this does it mean. This mean and what it doesn't. And finally, sort of as a recap of all these 3 days, I will present a series of studies in which you will see the methods and the concepts that I try to convey these days in action, in actual projects, with really producing results in different geographical areas, in different populations with different questions. And that this last part is really open-ended, because I was quite ambitious. I piled up something like 60, 70 slides. So but strategically, they are in decreasing order of relevance or importance. So at one point we may call it a day. So let's start first then with descriptive statistics in population genomics. We will first, kind of logical, describe variation within a population. We'll see measures for that capture just one number diversity within a population, and we can do that in different ways. And we can have a rule function, which is the side frequency spectrum. And then we will compare populations through PCA, UMAP, and we may add, and I forgot about that, and I'll mention it in passing, even if you didn't get some slide, MDS, multidimensional scaling. Then a mixture, not the concept, but the program. And then, since there is more information in haplotypes than in single loci, we will see methods that work with haplotypes, and you will see that you can do many different things from data once you take into consideration the haplotype structure rather than single SNPs as one would do in agriculture or PCA. So, how diverse is my genome of interest? First is this by itself is not that interesting if we don't have reference point. Because otherwise, what does a number mean? We'll usually have a number of different populations and a number of different ways of measuring diversity. And obviously, what we will do is we will compare that. But if we do that with this table, we will just eyeball it, okay? In the sense that here, for instance, we have 0.16 and 0.17. And we can say that the things like these two numbers are similar. These two numbers are similar to one another. I have to mark with a cross here. I suppose. Yeah.
You can use the circle in the ground as
Yeah, here. Okay. And so we can say that this 16 is similar to this 17, but this is not a statistical test. It is single. And you can say that this population has twice the value of that other population, but again, this is not the test. Okay, so what are these columns here? We have here sample size, number of different haplotypes. This is mitochondrial DNA, so sometimes there are some types of variation that you can count or you cannot count. So this is the difference between these two columns. Of course, number of different haplotypes is strongly dependent on sample size. So by itself, it doesn't tell us much. This is nucleotide diversity, and we will see nucleotide diversity in a minute. And we will see that it's exactly the same thing as MTD, which is the mean pairwise difference. And we have S, which is the number of segregating sites, number of polymorphisms, which again is strongly dependent on sample size, unlike pi or MPD. These two figures here, again, I put them aside because they are concepts that relate to forensic genetics. I might as well say that these are the randomized probabilities. Again, depending on how counter or on how one defines a haplotype in mitochondrial DNA. So we have then in other the different variations of the heterozygosity thing. We can average heterozygosity per site, and this is the nucleotide diversity. This just means we measure heterozygosity at a given base pair, go to the next one, complete the same, then average. And of course, many, like 99.9% of the sites will be monomorphic in any given population. So this will be a rather small value. We can count, given any pair of sequences in the population, by how many nucleotides they are different, and then average that over all possible pairs. And actually, we will say mostly empirically that L and with L and sample size this is just a function of pi. We can go one step further and look not at the average pairwise difference, but to the pairwise difference distribution. And that was really one of the few things that we had for demographic inference with mitochondrial DNA sequences in the 1990s. And we can extend the concept of heterozygosity to all haplotypes. Does this individual carry the same haplotype in the two chromosomes? Then homozygote, heterozygote. Okay, we're just talking about Hardy-Weinberg's law. Under a number of conditions, since what you inherit from your father and what you inherit from your mother is independent from one another, then the proportion of homozygous is the frequency of these allele squared. Same thing for the other homozygous. For heterozygous, it seems we don't know which is which. We have to count them twice, and then it's twice the frequency of one allele times the frequency of the other allele. And we can work a little bit on this, since for a biallelic locus, the frequency of one allele will be 1 minus the frequency of one allele of the other allele. It can be easily derived. Oh yeah, there. So the complexity is 2p 1 minus p. So this is 2p minus 2p squared. So in mathematical terms, this is the equation for a parabola. And if you use your high school calculus, you will find out that this function has a maximum at p equals 0.5. So maximum heterozygosity, maximum diversity at 50-50 allele frequencies, and everything goes down from there. So then, even with this simple relation, you can see how heterozygosity is by itself a measure of diversity. So if we have a sequence of length L and S polymorphic sites, nucleotide diversity by, recall that it's the average heterozygosity per site, would be since 2 is constant, we take it out of the sum. The allele frequency at each site times 1 minus the minus the same allele frequency over all sites over L. We can save many calculations there. We can restrict this to the S polymorphic sites, but we still will have to divide over L because it's an average over all sites, independently of whether they are polymorphic or monomorphic. And human pi is sounds like a pi made of humans. No, the average pi in the human genome is about 1 per 1,000, which compared to many other species is quite a small value. If we could plot here the distribution of pi across, say, mammalians, human pi would be, I don't know, in the first 5% of the distribution, something like that. And this is a testament to the small effective population size in humans. We may look like 8 billion people in the planet right now, but our genomes tell the story that on average, on harmonic average, or at one point, the number of individuals who were reproducing were just 10,000. So this is the significance of life.
Sorry,
Yeah.
I'm not informed, by the way. So math is not my area, but time should not be taken into account in this formula or in this account.
Time.
Yes, because the longer the time passes, maybe sites could be more polymorphic.
No, this is a snapshot of the diversity in your sample right now. Look how I'm using it. I have here mitogenomes in these populations. This is actually in Paraguay, not. So I computed pi for all of them. So I can say these two are not very diverse, maybe similar to this one, and the other three are more diverse than the other. But right here, right now, in these samples, we are characterizing diversity through average look at heterozygosity in our samples. What you are suggesting is how should we model the expected value of pi? Yeah, and for that you would need time and you would need effective population size, and mutation rate, of course.
I was wondering if today we exclude from this kind of analysis not biological class because of our mathematical limitations, or because it's
no, it's just no, we are not excluding. We are excluding them just because I'm lazy. Of course, this you could extend this. Of course, this is an equation that works with biallelic SNPs or any type of biallelic marker. We could extend that where then we should have here another sum with this product for every allele. P times 1 minus P for all the different alleles one has, or maybe it's probably easier to express heterozygosity as complementary to homozygosity, and then you would have 1 minus the sum of the square of all the different allele frequencies in your sample. And of course, that's how you would do it. For instance, with STRs for tandem repeats. But the concept is the same. It's just and you can apply it exactly the same. It's just that the equation is slightly more complicated. But it's sorry, I forgot to I forgot to mention that this is nucleotide diversity, and the name itself implies SNPs. For an STR, we would call that average expected heterozygosity. But it's the same. So, and it's the same, although it doesn't look like that. When we count differences in the count the differences between two sequences. Here we have these short sequences in which I have highlighted the say the alternate alleles in each sequence, so it makes it easier to count. For instance, A and B are different at this position, this, and this. At this, they have 5 differences. This is Sesame Street population genomics now. Between A and C, we have 1, 2, 3, 4 differences. Between A and B, we have now 1, 2. These are the same. So yeah, we have 1, 2 differences, and so on and so forth. So now we average these 6 values. We don't need to compute either half of the matrix because it's exactly the same. And it comes to this figure here, 3.167. So on average, these sequences are different at 3.167 sites. Now let's compute for the same exact sequences by nucleotide diversity. So we have this and this and this 3 and this 3 and this for monomorphic, and their heterozygosity will be 0. We have 90 sites, heterozygosity 0. we have 5 singletons. This one, sorry, this, and this. We have since singleton means we only see one allele over 4 sequences, then P is 0.35. Then the heterozygosity will be like the formula 0.375. And we have this doubleton here, and this doubleton here. So this means the allele frequencies are 50%. So we already know that heterozygosity then is 0.5. So pi then would be the average of along all the sides. So it's 9 times 0, 5 times 0.375, 1 time 0.5 over 15 possible over 15 sides. That's the average is 0.583. That's fine. Now take pi here, multiply by L, and adjust this for sample size, and we get exactly the same. So the relation between mean pairwise difference and pi is just quite immediate. It depends only on L and sample size. There's a mathematical demonstration for that, but believe me that there we will be spending our time better if we move along a lot. So if you ever compute mean pairwise difference and pi, don't discuss them separately, as I see sometimes in papers, because they are the same thing. And here we have this average, but we also have distribution. Here we have this inline distribution in which 2 appears twice, 3 appears twice, and we have one case of 4 and another of 5. This is now for mitogenomes, the mismatch of the distribution in different continents, and you see just visually, no test yet, that African sequences are more diverse. If you take at random 2 African sequences, they will have quite a large number of differences, and whereas European and Native American have this big here and another there. And to give you a sense of scale, even the mutation rate in the mitochondrial genome, to get to these 80 differences, you need 100,000 years. And this is much less than that. This will be like 10,000 years. So at one point we were modeling like crazy these peaks and expansion and so on and so forth. Turns out that it's more complex than that. So yeah, sure. Here's an extension to multiple alleles, because usually you have more than 2 haplotypes. So yeah, for you can go for if we have k different haplotypes, then it can be shown quite easily that the haplotype diversity goes like this. And the problem then is that it doesn't have you don't have a clear expectation of the scale of, is this value, is this edge small, is it large? For that, we can make it relative to its maximum possible value, and it's and that's quite easy to compute. Logically, the maximum haplotype diversity will happen when every haplotype is different from one another. So this means that that you have that then K equals N. K, the number of different haplotypes in this situation, will be equal to the sample size, and the frequency of each haplotype will be then 1 over N. So, so then what? So this becomes this. Look, we are saying that that P is for every haplotype, the frequency will be 1 over N. So 1 minus P then will be 1 minus 1 over N. And this sum will be the sum of N equal values. It will be the same for haplotype number 1, number 2, number 3, up to N. So summing the same thing N times is the same thing as multiplying by N. So this is why there's no longer any summation, and that's how this N here appears. So this then this N and this N sort of strike each other out, and we're left with this. If every haplotype is different, then haplotype diversity, expected haplotype diversity comes to N minus 1 over N. So now, if we take our the edge value that we have observed and divide it by this quantity, we divide, so that's why it's upside down. Then now we have a measure that goes between 0 and 1. Now we are sure that if we have the maximum possible haplotype diversity when everyone is different, then now with this little tweak, now edge will go from 0 to 1. If we don't add this, then it would go to from 0 to N minus 1 over N. And since we may be comparing populations with different sample sizes, it will make the comparison not relevant, not possible even. So now we have seen all the statistics in this table, and it's not by chance that is done with mitochondrial genomes. So 2 reasons. Usually, one does not compute for entire genomes. Well, sometimes it's not that interesting. It's more interesting for shorter regions, for genes, for mitochondrial DNA. And for stuff like haplotype diversity, you need haplotypes, and this comes naturally in mitochondrial DNA because it is haploid. Of course, you could do it with nuclear genes, but we have to face them first. If you want to compute haplotype diversity, otherwise you don't need them. Funny thing, here we have haplotype diversity by another name, because we'll see in the forensic part that haplotype diversity in mitochondrial DNA is the randomized probability. Sorry, it's 1 minus the randomized probability. It's the probability that 2 individuals match at random. It's also the probability that it's 1 minus the probability that they are different, and the probability that they are different is haplotype diversity. So another turn of the wheel now with allele frequencies, we can plot them like this. The frequency of the derived invariant, and this is just counting how many sites have been in how many sites the derived variant has been seen once, twice, 3 times, 20 times, 40 times, 60 times. There are two variants. Strictly speaking, if this is the derived variant, then it's the unfolded side frequency spectrum. It means that it can go from 0 to 100%. If we count only the minor allele, then it goes from 0 to 50%. Minor as in the least, the less frequent allele. And one of the results that we got yesterday with coalescent theory is that the expectation of these of the number of sites that have an absolute frequency I is 4n mu, n should be of course ne, the times the length of the sequence over the absolute frequency. So you see that it contains information on any mu. And there are a series of methods that are used to divide and to derive what is the demographic history that would produce this particular side frequency spectrum. It was done first with ABC, which is approximate Bayesian computation. And now it's done with all kinds of neural networks and stuff like that. One of the researchers in our institute is an expert in this, and it's a peculiar type of guy. It's so modest that he will spend 90% of his presentation saying, "No, I cannot really do what I'm doing. This is wrong because of this or that. I have this and that issue." Well, Oscar, okay, we know, but you're getting wonderful results nonetheless. And you can do that with a single SFS or the joint FSS for two or more populations. You can turn this line into sort of a cube in which you have the number of SNPs in one population, the numbers of SNPs in the other population that have a joint frequency of this and that. And that carries a lot of information about the joint history of those two populations. Because of course, if they share history, they will share also alleles at similar frequencies. And you can also add a functional and thus selection aspect to the side frequency spectrum if we take into account the different functional classes, the usual non-total, synonymous, non-synonymous. And we already saw yesterday that non-synonymous SNPs tend to be rare because they are kept that way by negative selection. Since most biological systems are pretty well tuned, it's difficult to have new function variants that are really allowed by the system. These are the right alleles that went almost to fixation. That's positive. This is negative selection. This is positive selection here. So moving on now to comparing populations or comparing many individuals. I have I'm always with the mindset of describing data. I have a data set with many variables in many data points. This is a general problem in statistics, data analysis. I cannot possibly plot the data, say in a scatter plot. we can only see 2, maybe 3 dimensions. The books we used to have as kids that when will sort of like pop up. So you would need those to really have 3D 3D plots. So yeah, we are used to present and to read our information in 2 dimensions. But here, my data don't have 2 dimensions. They have 100,000 or a million dimensions. The frequency of each thing, and we need to plot that for say 100 individuals. Although 100 individuals is the least of our problems. Then this is a problem that has sprouted a whole branch of statistics called dimensionality reduction. How we shoehorn this number of dimensions into a flat representation in a way that still captures the diversity in the data and the patterns in the data. We have PCA for that. PCA means principal component analysis, which is kind of similar to regression. So the idea is that if our original variables are good, and this is statistics, we will come back to genetics in a minute. If the original variables are x1, x2, xn, then we will calculate these linear combinations. We will compute the A's so that with these multiplications and sums, there's nothing fancier than that. No integrals here. We will get principal component 1, which is, as you see, a linear function of the our original variables. But of course, you could invent as many different A's as you want. But we want the A's to do this. They need to capture the highest possible fraction of the variance in our data set, and they should be statistically independent from one another. Independence in statistical terms means lack of correlation. So it's I said linear combination. This means that the result is aligned. In this case, in this multidimensional space, but aligned nonetheless. In which here the blue dots are our original values, and we can compute this line so that we are now capturing most of the variation and projecting our original data on this line. We get the red dots, which are if we sort of turn this line as a single axis, this would be the coordinates for the first principal component of our data. But then we have this value here, the difference between this point and its projection, this point and its projection, this. We can work with that to extract the next principal component. This variation is independent, is a residual of what we capture with the first principal component. Yeah. So, what are our variables in population genetics? We can do this in 2 different ways. We can compare populations. Each dot will be a population, and the axis and the axis, original axis. You have 2 different words: the x and the axis. The original variables then would be allele frequencies. And this was invented in the 1980s by Luca Cavalli-Sforza and Paolo Minossi and Alberto Piazza. So this was different times. This is actually a photograph, a physical photograph of the screen where this was being projected. So here, what we see here is the sort of like the altitude lines, there's a word for it. The level you see when you see a cartographical map. Yeah, when you see a topographic map, there's the points that are at the same altitude above sea level are joined by a line, by a contour line. So this is the same since they had samples all over Europe. This is here the height, the darker versus the lighter colors represent the values of the first principal component, and that would be the second principal component. And at that time, they were using 38 independent alleles, 38. We were talking about millions. We're now in the data with millions, but they had the same problem. It's exactly the same problem if you want to represent 38 dimensions, and you want to represent 1 billion dimensions. It's not 2, you cannot see them. So they had 38 independent alleles at this low stereo. RH, MS is another blood group, so is Lewis, so is Duffy. This is the haploglobin. This is serum protein, EGM, that's an enzyme, HLA-A and HLA-B. And 10 years later, the method was still the same, but we could have nicer representations. This is the same type of plot now in this 3D, and we see how the blasts are appear genetically different. You see, this is the Iberian Peninsula. This would be Portugal. This is the Mediterranean. Can you see? Okay. Still, this is part of my doctoral dissertation, and again, I know I sound old, but I am. So bear with me. I had physical slides, and some of those were actual pictures of the screen. We had this black piece of cloth that we put on top of the computer screen, took a picture, and turned that onto a slide. Now, now we take the time machine that is life, and we come to the present. Now we do PCA in a different way. Now the original variables are no longer frequencies that go from 0, 10%, 20% up to 100%. They are genotypes. And a genotype can be a quantitative variable as well. You can add and multiply genotypes just by counting the number of alternate alleles. A genotype becomes then 0, 1, or 0. And now each dot is no longer a population, but an individual. So this is the superpopulations of a 1,000 genome data set, 1,000 genome database, and you see that this usual triangle in which we have here these magenta dots are Europeans. Who else? Here we have, these are not Native Americans, but population sample to the Americas. Remember that we have Peruvians, Colombians, Puerto Ricans, Mexicans. Sorry. In green here, with apologies to Any colorblind people? No? I was looking specifically at the men because you know that. Long story short, 10% of the men are colorblind, are particularly sensitive to this. I'm not, but I have two colleagues who are, and they would be cursing at me if I show that. I cannot tell red from green. So, and we have East stations in purple, and in this darker green we have Africans. It's this usual V shape, and this is there's nothing genetic in this V shape. Why a triangle and not another shape? This is just a result of this construct, this statistical method. And we are representing here PC1 versus PC2. So now we have this space, but of course we have many other dimensions. We can compute as many principal components as we like. So now this is PC1 versus PC3, and we see that this is probably what's appearing here that was not there is the Native American component, because it's found mostly in the Americas. It's found not all the individual samples in the Americans carry these get these type values, but still. With PCA, you can do a neat thing, which is quantify the amount of variance that every component captures. Let's say that overall the variance, statistical diversity that I have in my data is 100%. This is about 1–2% of value. And that's a huge value. Huge. 1%, huge. Why? Because if we have 1 million independent variables, each of them will capture 1/1,000,000th of the variance. And 1% is 10,000 times 1 million. So what PCA is doing here is capturing the what PCA is doing here is capturing internal correlations between these states. Who goes with whom? Which the Africans here appear different, appear in its, at the extreme, because they have the larger number of snakes with private or semi-private alleles. But still, 1% means that we are not seeing 99% of the overall variation. 99% of the overall variation is not structured in continents. There's still lots of variance that we don't see, and that they don't have this particular shape. But still, this is even though it's small, it's the main source of variance. Now a neat trick. This is, I found this by chance. Let me count here. Now, try to cross your eyes. So as you try to overlap the blocks. You cross the eyes. How am I looking? Oh, yeah. Are you saying that can you see that the magenta and the purple come to the front? Well, I guess that it's not meant to be done at this distance, but I assure you that looking at the computer screen, you can manage to do that and really make these two then pop up and what the other did here is represent as this depth, the third principal component. This is just like a fairground trick, but still, I found it neat. It's the first time that I present this, so I know I wasn't sure that it will work in a classroom. But if you go there, or if you have to do the presentation on your screen, maybe the people following online are managing to see that. Now there's a new method. No, sorry, there's another thing. Something else that we get from principal component analysis is that the program that computes them gives also the values of the A's. And with that we can do another neat trick, which is if you have MTDNA, most likely you will have many missing values. So the quality and degradation of the array. But still, you have these equations, and these equations allow you to plug in the genotypes that you do have and ignore the others. If you had put these ancient genotypes from the beginning in the calculation, you then would have needed to drop all the variables that have missing values from the analysis, and maybe imagine that each individual has 10% missing values, but they probably are not the same from one individual to the next. So if you have 20, 30, 40 ancient samples, you would be left with nothing. If you really made the set of of variables without any missing value. So what you do here, this is quite common practice in ancient DNA analysis, is that you have modern samples with really few missing values. You can do that with DNA of perfect quality, get your results, compute PCA, get the A's, and then for every single ancient sample, you compute that with the non-missing values, specifically with the non-missing values of each sample. So then that's called projecting. So now we can project each ancient sample on top of the modern variation. And the next thing is that sometimes, like here, you see them outside the modern variation. Means that there was some ancestral component that did not arrive to the present. And sometimes you see them used, and the neat thing is that you see these dots moving in time and getting to the current location. Yeah, this is an example from the Iberian Peninsula. These are all ancient samples, and the color will represent the archaeological time from the Paleolithic to the Middle Ages. And you will see that I don't know. Let's imagine that the Middle Ages is this purple color. I don't know if that's the case, but you would imagine that the purple dots are already quite close to the current location of the people currently living in Spain and Portugal. Now, the new kid on the block, humor. This is becoming quite. It's a little bit more complicated. It's kind of fancy pants. It's a new method of dimensionality reduction, and it's quite common and it's been adopted, particularly for the transcriptomics community. When you do stuff like single cell transcriptomes, you have RNA expression that they are doing for thousands of cells at a time. When you do first that big thing that can separate cells one by one. I can't remember anyway. They do that, and the difference between UMAP and PCA is that UMAP tends to emphasize vicinity rather than difference, and it will cluster who's the same all together. And this is an example. This is actually my face when I saw this label here. These are, and this is the type of shapes, because UMAP emphasizes neighbors. So these are the 2 dimensions of UMAP. UMAP works also with genotypes. And the colors here, each teeny tiny dot would be one individual sampled in New York City. And they have colored each dot by this non-biological category called race. Think about race. Race exists. Otherwise, racism wouldn't exist. There are social categories of people who feel that they are superior to people to other categories. And this is a concept. Well, it's not, but it's quite in the modern sense. It comes from places like New York, like New York City. And there would be a category in this race thing that would be Hispanics. So that has to be without just conceptually, without going to the actual data. What does being Hispanic, whatever that means, to have to do with biology or genetics? I could, in my particular case, I wouldn't know. I wouldn't exactly know which category should I check in an American forum. Most of you either. You may be Latinos, but you're not Hispanic. Then, and I may have the Spanish nationality. If that's one criteria for being Hispanic. But my mother tongue is not Spanish; it's Catalan. So again, which box? So here's the thing. Races are social constructs. Are they mirrored by genetics? First, we have this difficulty. Even if ignored it, the answer is that, and we will go over again this in the next lesson. Is no. Because first, we tend to sample at extremes. If you start walking from Barcelona towards the east, and you won't stop until you get to, say, Beijing or Shanghai, you wouldn't know you wouldn't be able to draw a line on the ground saying Europe or people who look like me finishes here and Asia starts there. No, it's a gradient. I once met a lady from the Inner Mongolia who, to me, to my European eye, looked Asian. She says that the Han Chinese thought she was European. So, human genetic diversity doesn't exist in neat little discrete packages. It's continuous. Sometimes the change is sharper. Of course, you have the Sahara. Sahara is to process, to marry and have children across the Sahara. There are, of course, areas in which the genetic change is sharper. But remember what I told you. The difference between Europeans and Africans is 1% of the total variation. The main source of variation we have is a single individual. Another argument on that. Then, if that's true, how could the people at 23andMe guess my geographical origin? They just said, oh, you are you, but the people whose genomes look like yours happen to live in Spain. It's not incompatible one with the other. Another argument for what's called now scientific racism. Why aren't human? If we called I don't know, a German Shepherd and a Pekingese as different races of dogs, why don't we? Why won't you accept that humans have races? Because the amount of differences we have between dog breeds is huge compared to the geographical differences in humans, and they have accumulated that at a very short time. And for a more important reason, again, race is a social construct. Who belongs to which race is not, to a large extent, it's not determined by their genomes. To some extent it is, but it's not at all perfect. Moving on. MDS. Poor thing that it didn't get its own slide. There's a third multidimensional scaling. It's a third dimensionality reduction method, which works with distance matrices. If you have a distance matrix between populations or between individuals, and in a minute we'll see one of those. There's this MDS method that would allow you to plot the points on a plane so that the distance along this representation, along this plot, is as similar as possible to the original distance matrix. And it allows you to work then with genetic models to base your definition of a distance in genetic concepts. Say to have, for instance, measures of distance that are proportional to drift. Let me show the program. There's this statistical question. If there existed k different populations in the data set, what is the probability that each individual would belong to each one? Imagine there are two populations. Given your genotypes, what is the probability that you belong to one or the other? Or, and there's a first thing, which are how do we construct two populations so that we can classify individuals in one or another. Thus, you can do that, and make sure the program does that. It's sort of the successor to a different program that was used in the beginning called structure. Now for the last 10, 15 years, we've been using a mixture. Now, your question is relevant. Structure takes multi-allelic loci, mixture doesn't. And these are the results. Again, for the Populacional project, if there were 5 here, each vertical line, you have to imagine teeny tiny, really narrow vertical lines. Each line would be an individual, and each color would represent, in this case, we have 5 different colors. And this individual from the Luya in Kenya would most likely belong to the yellow population. These individuals from Nigeria would have a probability almost 50% of belonging to the yellow or the red population. Here we get to Gambia, and they are mostly red. The green color is more. This green component is found mostly in European population and in the Americas. Blue is East Asian. Is most found most often in East Asia, and light blue in South Asia. Now, when we add another color, they have to change. Now it's like this. Do we have this? Now this sort of light blue looks like, that most likely this is the Native American component. If we add another color, who are you, where are you? I don't see it right now. Anyway, these are colors. These are not real populations. We shouldn't forget that these are statistical constructs. And it's quite easy, and it happened to me right now, to slip into saying that this is the East Asian component. This is the component that is most frequent in East Asian groups. It's not the same thing. Again, this is the description of the data, and this is not actual populations, but statistical constants. And we can compute the cross-validation error, and we K with the lowest cross-validation error gives us the better partition. This case is this is about Madagascar, and this is telling us that the best representation is with 3. Usually, we tend to like 4 or 5 better if we have explanations for those. But anyway, in this case, the best is the number of components would be 3. And here's an example of an MDS plot. And IBS would be identity by state. There are issues with the mixture. Components are not real populations, just statistical contracts. Large samples, this mixture is quite sensitive to sample size. So large samples will tend to hog its own component. So quite often it's good scientific practice to subsample large populations, so that all the samples have similar sizes. And isolated populations tend to get their own component more than you would reasonably expect. Now, up to now, we have been working with single SNPs and avoiding avoiding haplotypes. Actually, in a mixture and in PCA, we filter first those variants that are at high linguistic equilibrium with one another. But there we are missing information because you can combine different SNPs in many more haplotypes than there are SNPs. For instance, 3 SNPs have 6 different alleles, but those can be turned into 8 different haplotypes. So, can we do something about using haplotypes? I won't go into the details, but there's this tool, this program called Chroma that basically finds shared haplotypes between individuals. And here, yeah, it would, yeah. So I wouldn't go into the detail. So now, with these shared haplotypes, we can do many things. For instance, these are both in the rows and in the columns, we have the same set of individuals, and the colors represent how many haplotypes they are sharing. So we see that this group of individuals here are closely related to one another because they share lots of haplotypes. And we can turn this into a tree, although we don't like trees. And with this coalescence matrix, this number of shared haplotypes, we can cluster them with the program called fine structure, we can do PCA, and with Globetrotter, we can do admixture estimates that are now based on shared haplotypes. So here's an example in the Netherlands. We have the coalescence matrix here, place this clustering, and we can do PCA now not on single SNPs, but on shared haplotypes. And kind of looks like the map of the Netherlands. And again, based on who shares haplotypes with whom, we can turn these to estimate the mixture events with timing and composition. This is no longer fictional populations. This is no longer a mixture. Now we are actually testing whether we can produce one particular population as a combination of others, and what time should have elapsed to get what we see. And that's the end of the first outline questions.
I have 2 operational and questions and 1 more. First of all, is MDS and PCA equivalent?
They tend to give the same results, but they are statistically different. You can do PCA with the shapes of potatoes. You could have different breeds of potatoes, measure different things on those, and plot that as a PCA. With this, my point is that PCA does not by itself incorporate any type of genetic model, but you can incorporate a genetic model into a genetic distance. Say, for instance, you can devise a statistical distance so that it captures the amount of drift that's required to produce the differences that you see between populations. And then you can use MDS to turn that into a bidimensional plot. So now you have something that you have a method with genetics as a feature. Having said that, the results tend to be quite similar.
Use MDS for analytics. I don't think we put a specific genetic model, just run the MDS.
Yeah, to run MDS, you need a decent matrix for it.
We calculated the matrix in R, and then
That matrix would have been FST, and then you have a net.
the second question is about admixture. We were used admixture too, and we run both analysis unsupervised with consolidation for knowing the best key at K number, and then we supervise with the one KGT, one KGP populations. So my question is, even with the supervised analysis, the population are still visible.
Well, then in that case, you are asking how likely it is that that each of my samples could belong to those references. In a sense, you are closer than to real population, but you are doing something else. Is that you are forcing your samples to be like those references. If they have something peculiar to themselves, you wouldn't see it. So it's sort of a trade-off.
Never thought about it. Thank you. And the last question is more theoretical, because when we run the MDS for the 1 kg samples, we saw that South Asians tend to accumulate together with Americans, here.
Yes.
So, and
They would separate. My guess is that they would separate in the 30s of the body.
sorry.
They would separate in the MDS. Can be you can have 2 dimensions or 3 dimensions or 4 dimensions or whatever. I better be that they would that South Asians and Native Americans would separate in the 3rd dimension.
I thought about it, and we were thinking why, if it was like we got a little bit crazy, we were thinking like possible convergence evolution in that portion of.
Yeah, no, both are Indians. Yeah, seriously, no, it's there's so much structure that you can show into dimensions.
Thank you.
More questions? Okay. Keeping with tradition, we break now for 15 minutes. Back at 35.
Yeah.
Back at 3:35.
3:35.
Voltaremos 3h35, pessoal.
Next slide of the haplotype and the global focus for little mind blowing. I want to interact with you, but I'm still here. Thank the visit and rest of the people.
You know,